Hello everyone, it is me talking about internal resistance. I'm going to make this as quick as possible because I'm doing this again because the first run through was 20 minutes long and it was so insanely boring I couldn't listen to it all. So if I can't listen to it all, why should you listen to it all? So you're going to pause this video as you go through it, and I would write down all the notes I've written down, or make your own. I'm not going to waffle here. I'm just going to read through my notes and then you can get on with the work. The resistance of the power source is what is called internal resistance. And just as work is done by charge as it flows through a circuit component, so also work is done when current flows through the power source. Some of the energy is lost as heat. The power source heats up the battery and therefore not transferred to the external circuit. So basically batteries, power supplies have their own resistance associated with them, and it's called internal resistance. Let us look at what effect this has on the amount of voltage that's available. The current through power source with internal resistance R causes a PD referred to as lost volts across the internal resistance. So you get the idea? When you have a current flowing around a circuit like this, current through resistance creates potential difference across it. So just as you get a PD across this external resistor, so you get a PD across the internal resistance. This PD across the internal resistance, the resistance of the power supply, is referred to as the lost volts. V equals IR. In terms of lost volts, it's this little r, this lowercase r, is the symbol for internal resistance. A cell, let's say, has 1.5 volts written on it. It's its EMF, but when connected to a circuit, some of the EMF is lost. It turns up as lost volts. Look at how this works. Here's our EMF, curly E, big E, 1.5 volts. Here's the cell within its little internal resistor associated with the cell. This is all the battery. This is not a separate resistor, it's just a symbol for the internal resistance of the cell. Let's say it's 0.10 ohms. Connect it to a 3.3 ohm resistor. How much of the EMF, 1.5 volts, is lost across the internal resistance? Let's have a look. Let's work out the current first so that we can then work out the PD across the internal resistor, the lost volts. The current around the circuit is I is V over R. In this case, it's the two resistors added together. They're in series, right? So it's 3.4 ohms, 1.5 volts EMF across 3.4 ohms gives us 0.44 amps. Then we can work out the lost volts because it's 0.44 amps flowing through this internal resistance. V equals IR equals 0.44 times 0.10 is 0.044 volts. So the PD across the external resistance is going to be the EMF minus that voltage across the PD across the internal resistance, which is going to be 1.46 volts. Let's see how that works. Here's a word equation that generally sums up what's said so far. The EMF is equal to the terminal PD, that's the PD in this case across the external resistance rather, which is the same as if you measured it at the terminals here of the power supply, because look, it's the same PD, isn't it? Ignore this switch, that's something I did earlier. We also had a spider crawling across the page earlier, which I'm afraid unfortunately won't feature in this video because, that's not a long story, but it's a very sad story. So it's 1.5 volts minus the 0.04 volts. So the terminal, oh, I did that, didn't I? Sorry, let's just do this equation. EMF is the terminal PD plus the lost volts. That PD plus that PD equals the EMF. Now, this terminal PD is measured across the terminals of the cell. That's why it's called the terminal PD, everyone. And it would be 1.5 volts if no current was flowing. Because, why? Because if no current's flowing, no PD will exist across the internal resistance. So no PD will be lost. So you get your 1.5 volts. Well, but that's not much good, because if you're not having any current flowing through the power supply, it's not doing any work. It's not conveying any power to anything else. It's not connected to a circuit, or if it is, the switch is off and the current's not flowing. So big deal. So in practice, you always get some lost volts. Here, let's carry on, see if I can get to 10 minutes here. Less than 10 minutes, that's the aim. EMF equals terminal volts, big V, plus lost volts. Lost volts is I little r. Terminal volts is I big R. V equals IR. V equals IR. So this is true. EMF equals this I big R plus I little r. Simplify, put it in brackets, these two R's here. That's big R is the external circuit resistance, little r is the internal resistance. Here's the experiment that you can do. Here's an experiment that you could do. So you set up a circuit with a cell, a variable resistor, an ammeter and a voltmeter across the cell. By varying R, we can record different values of I and V. See page 180. As you decrease the resistance, what will happen to the current? It'll go up. And as the current goes up, what will happen to the PD across the internal resistance? It will go up. It's really just a potential divider dividing the EMF across these two resistors, the external and internal resistance. But it's not a very helpful potential divider, because only one of the resistors is external. So, you know, it's useless. Anyway, but it's in principle a potential divider. You would plot, look at all this, you'd get a graph like this. You'd plot V on the y-axis and you'd plot I on the x-axis, and then straight line graph, y equals mx plus c. Rearrange E equals V plus IR for V, you get this. Turn it around a bit more and swing that around into the form y equals mx plus c. Plot V on the y-axis, plot I on the x-axis. Your gradient is equal to minus r, and your y-intercept is equal to the EMF. That's what you would get. Let's do a question. Let's suppose we've got a 24 volt battery with a 100 ohm resistor and 0.20 amps is flowing. Let's work out the terminal PD. It won't be the EMF. It'll be less, because some of the 24 volts is lost across the internal resistance. Right, so let's work it out. V equals IR. Terminal PD, we want the external resistance. That times that, 20 volts. Oh, what's the lost volts? Well, the EMF is 24 volts. The terminal volts is 20 volts. The lost volts is therefore 4 volts. It's the difference between the two. 20 volts across here plus 4 volts across here gives us our EMF. Remember the equation? And then what's the internal resistance of the cell? Well, you just use your R is V over I. In this case, V is the lost volts, 4 volts, divided by 0.2 amps gives us 20 ohms. I'm going to come in under 10 minutes because this refers to this page, these 5 pages. That's a big topic, this. 177 to 181 do the plus box, do the green box, do the questions, enjoy. Over 10 minutes. Damn, never mind. Stay safe.